Hi all, this is Lakshmi working as assistant professor in the Department of ECE at SNSCT. So today I'm here to discuss about the case study on analog front-end design for biomedical sensors. So here we are going to focus on the ECG, that is electrocardiogram, so which records the activity of the heart. So the main objective of this case study here is to design the analog front-end circuit which ensures accurate and reliable acquisition of the ECG signals, which minimizes the noise and interference and also maximize the power efficiency. So we all know that every human cell is acting as the tiny battery. That is, it is a voltage generator due to the ions present inside the cell. So each cell is generating the cell potential. So we call that as the biosignal. So these biosignals are captured or picked up with the help of the electrodes, and then it is given to the recording setup for the signal processing. So here when we focus on the ECG, that is which is recording the activity of the heart, the points where the electrodes are placed in this case will be the right hand, that is the right arm, and right leg, left leg, and then chest. So these are the 5 points where the electrodes are placed and the signals are picked up and it is given to the ECG recording setup. So here we can see the normal ECG waveform. So it is represented as P, Q or S, T. So this is the normal ECG waveform. So the interval between this P, Q, or S and T should be the same. If there is any variation or if there is any delay in the occurrence of this point or these points, there occurs various heart diseases like coronary malfunction or myocardial infarction, etc. So based on this analysis of the ECG waveform, the doctors can identify the various types of heart diseases. So here we are going to check whether this acquisition of this ECG signal is noise free and without any interference, and the power efficiency is also good in this case. So, biomedical sensors plays a crucial role in monitoring and diagnosing various health conditions. So, as I told, this case study here is going to focus on the design and optimization of the analog front-end circuitry for biomedical sensor, specifically targeting the development of an ECG monitoring device. So there are certain design considerations while designing this analog front-end circuit for ECG. So the first parameter here is signal conditioning. So we have to implement the circuit such that the weak ECG signal is amplified and it is filtered to enhance the signal quality. And then we have to consider the electrode impedance monitoring. So here this system checks whether the impedance monitoring is done such that it can ensure proper electrode skin contact. So providing the real-time feedback on signal quality and if there is any need to reposition also. And the next parameter is noise reduction techniques. So here we have to check the common mode rejection, filtering and shielding in order to minimize any interference from the external sources and internal electronic noise. So the amplifier should have high CMRR, that is common mode rejection ratio, so which has the ability to reject the common mode signal. And the next parameter to be considered is low power consumption. So we have to optimize the circuit for low power consumption in order to extend the device battery life. So such that the ECG monitoring in case of portable application will be better. And the next is the patient safety. So we have to ensure the safety of the patient by implementing the isolation between the circuitry and the patient to prevent any electrical hazards. So now moving on to the circuit architecture. So keeping in mind those design considerations, so we have to design the circuit in such a way that we use an instrumentation amplifier which has high precision and high common mode rejection ratio. So those design considerations should be kept in mind while designing the amplifier stage. So as we have discussed about the CMRR and the precision, we go for instrumentation amplifier and the low pass filtering. So we require this low pass filter to eliminate high frequency noise and preserving the original content of the ECG signal. And the next we implement high pass filtering. This is to remove the low frequency noise and ensuring the correct representation of the ECG waveform. So next is impedance monitoring circuit. So as we have told that the electrode skin impedance should be monitored such that the patient is recovered from the any electrical hazards. Sorry, prevented from electrical hazards. And this isolation barrier like optocouplers or magnetic isolators to ensure the patient safety to prevent the flow of current between the patient and the device. So this is the normal ECG waveform as we have discussed. So at the normal heart rate of 60 to 100 beats per minute. The challenges and the solutions. So as we have told, the first thing is the motion artifact rejection. So here the motion that is we go for adaptive filtering techniques to remove any noise present in the ECG signal. Then comes the flexibility for multiple leads. So based on the need, the ECG recording setup, there are multiple leads here that can be accommodated. For example, 12 lead system. So there are two different types. One is unipolar and the other one is bipolar leads. So based on the need, this accommodation of multiple leads has to be ensured here. So the next is the validation and testing, which is very important phase here. So we have to perform the extensive bench testing to validate the performance under various conditions. That is, the front end circuits performance has to be monitored like different heart rates, signal amplitudes, and noise level. And the next is the human trials. So we have to conduct the clinical trials involving human subjects to assess the analog front end's performance in real world scenarios such that we can evaluate its accuracy, reliability, and the user experience. So this is the common recording setup for ECG. So as I told, the right arm, left leg, and right leg, and the chest. These are the 5 points where the electrodes are placed and the signals are picked up and given to the defibrillator protection circuit. So here this part is going to have the buffer amplifier and overload protection circuit to prevent the patient from the electrical hazards. And then we have lead selection logic. So as we have told, there are two types, bipolar and unipolar. So based on the need, the lead selection can be done. And we have a calibration circuit in order to prevent any errors present in the circuit. We have an amplifier circuit which will boost the weak signal and is given to the power amplifier. Here in the output display unit, we'll have a pen motor which requires high power to write the signal over the CRO. So hence we have power amplifier. So this is the overall setup of ECG recording. So thus this case study has demonstrated the process of designing the analog front end for a biomedical sensor. So which focused on the importance of precision, reliability, and safety. So the successful implementation of this AFE ensures accurate ECG signal acquisition, enabling effective monitoring of cardiac activity in various healthcare settings. So this case study provides valuable insights into the challenges and solutions associated with designing the analog front-end circuits for biomedical applications. Thank you.